Okay, ma'am, I'm ready. You just let me know.
Yeah.
I'll start presenting. I'll
Just in
start
few
presenting.
seconds we'll start.
Yes. Ma'am, is the slide visible?
Yeah.
Yes.
Okay, you just let me know, and I'll start after the welcome address.
You just start.
Okay,
A
can I
very
start, ma'am?
No, let me start first.
Yeah.
Okay. A very warm good morning to our guest, Gopikrishnan T, Assistant Professor, Department of Civil Engineering, National Institute of Technology, Patna, Muhammad Sayeed ul Hasan, Assistant Professor, Department of Civil Engineering, Aliah University, Kolkata, Dr. Shruti Kanga, Coordinator of Center for Climate Change and Water Research, Dr. Suraj Kumar Singh, and dear faculty members and all who are here present from different walk of life. I, Priyanka Roy, welcome you all on behalf of Center for Climate Change and Water Research and Suresh Gyan Vihar University on this esoteric webinar on remote sensing and GIS for urban studies and environmental modeling. We are very delighted and eagerly looking forward to have you all involved in this quest of embracing knowledge. Now, today's webinar is on the occasion of 75th year of our independence, and the aim of this event is to sensitize the community about the recent conservations and planning strategies and obtaining views from academia, scientific research groups, industries, and different stakeholders on a holistic approach, which we will try to attain to understand in this webinar. Now, on this note, I would like to invite Dr. Suraj Kumar Singh of Center for Climate Change and Water Research to take forward today's event with a welcome address. Sir, you're most welcome.
Thank you, Dr. Priyanka. Good morning, everyone. Greetings to one and all present here. I, Dr. Suraj Kumar Singh, Associate Professor, Center for Climate Change and Water Research, welcome you all. It gives me immense pleasure to grace all of your presence in the interest of the entire community. It gives me tremendous happiness to present the welcome speech among the most esteemed people present over here. Before we begin, today we are conducting a national webinar entitled Remote Sensing and GIS for Urban and Environmental Modeling on the occasion of the 75th year of national independence. I would like to express my heartfelt gratitude to all of you who sincerely committed to this event to make it a grand success. From this platform, I would like to give a brief about the university and Center for Climate Change and Water Research. Suresh Gyan Vihar University is one of the most prestigious universities located in Jaipur, Rajasthan, India. It is the first private university in the state of Rajasthan that has been accredited by NAC with grade A. The university has students across the world in the field of engineering, sciences, management, pharmacy, liberal studies, hotel management, education, agriculture, and healthcare. And now talking about the Center for Climate and Water Research that aims at R&D activities and has got a lot of publications as books, research papers in reputed publication houses like Springer, Taylor Francis, Wiley, Elsevier with high citations. Faculties who are working in our universities are from premier national Central University, Wadia Institute of Himalayan Geology, Birla Institute of Technology, Mishra, etc. And about the courses that we are offering at our university, especially for my center, we are offering three courses. From bachelor, we are starting with geology. At master's level, we are having MSc Geoinformatics as well as MTech Geoinformatics. And thereafter, we are having PhD in Geoinformatics and allied discipline. Now the center have active participation and also regularly conducts conferences, webinars, seminars, workshops, so that the various academicians, scientists, research scholars from various organizations got a platform where they can exchange their research and finally they can come up with a solution that can help the community and the society, because at the end of the day we have to sensitize the community. The webinar purpose is to sensitize each and every individual, and the webinars are organized and conducted for the general audience to gain insights and information that remain effective in their lifetime exercises and the work. Present training program was changes taking into the mind of the need of the youth and the time. Resources like air, land, forest, and water are very important for the progress of the society. Is the prerequisite for the sustainable growth and towards the achieving the maximum sustainable development goals. The aims and the purpose of the webinar is to demonstrate knowledge, information, experience, all resources for the sustainable management of natural resources. We are very fortunate that we have received a large number of participation across the world, huge number of positive responses we have had. And with this, I'll hand over the session again to Dr. Priyanka for further proceedings. Dr. Priyanka, please.
Thank you, sir. Thank you for such a concise brief about our university and the center. Now, I take this opportunity to give brief introduction of our guest that we are honored to have. Gopikrishnan T, Assistant Professor from Department of Civil Engineering, National Institute of Technology, Patna. He did his Bachelor of Technology, that is BE, from Raja Rajeshwari Engineering College, Anna University, Chennai, followed by ME from College of Engineering, Gundi, Anna University, Chennai, and currently he is pursuing PhD from the College of Engineering, Gundai, Anna University, Chennai. He is a passionate and motivated young researcher and is part of International Society of Photogrammetry and Remote Sensing. He holds several key administrative responsibilities as Professor in Charge Survey Laboratory, Professor in Charge Sports, and many more. He has several research publications by reputed national and international journals, and he is a strong believer in interdisciplinary research. His area of interest and expertise is in the field of climate change, environmental and natural resource management, and many more. Now on this note, I would like to invite Gopi Krishna T to take forward today's event. So you're most welcome.
Thank you, ma'am. Thank you, sir. Especially Dr. Suresh, sir. Suraj, sir. So now I'm going to present you in a topic of soil erosion modeling using GIS and remote sensing. So this title is actually will be described to you with reference to Baraka River Basin in the Jharkhand state of India, and this presentation is actually it will be a case study, and also it is a project carried out by Mr. Akhil Malhotra, who is my PhD, who is my PG student, who has completed his MTech, who has defended his MTech thesis. I'm going to present you the title of soil erosion modeling using GIS and remote sensing, and I feel happy to share with you people about the knowledge what we have gained, and I hope that definitely this will be useful for you for carrying out your future research as a student and also as a faculty, right? So we'll start the session. So this will be the entire overview of the content that I'm going to present today for you. So first we'll be going through the significance, introduction, and we'll be having an overview of the study area, methodology, and results. So we'll start. So first of all, significance. So soil erosion is an important phenomena which happens by nature, and also mostly it is induced by human beings. So when the soil gets eroded, actually it affects the agriculture as an industry and also the natural environment. And topsoil, when it is getting eroded from a particular area, it loses nutrient-rich layer of the topsoil, and it will reduce the soil quality of that particular area. So when the soil loses its topsoil with its nutrient-rich layer, it will result in reduced agricultural growth and production. And also the construction of reservoir block the flow of sedimentation towards the downstreams, is getting blocked, and due to that reason, the reservoir will become as a source of sediment, where the useful sediments or the nutrient-rich sediments are getting deposited in the reservoir year by year, every time when the river is getting flooded. And when so here there are many more models which can be studied for soil erosion modeling, and the efficiency of model depends upon the landscape conditions and the data which is available. So here in this title we are going to see about the application of remote sensing data through the GIS software. It will be processed, and the final output will be a model that will be able to give you the quantification of soil erosion, and the possible locations of soil erosions can also be modeled. Uh, so here the top layer of the earth is actually, it is called as soil, and it sustains life. So on the top soil or the top layer of the soil, we are performing all our activities, and the soil erosion is actually a process where the soil particles will get detached, and it will get transported by the erosion action caused by wind, water, or any other parameters. Mainly water and wind plays an important role in the erosion. So here when you're talking about the particles of the soils, they will get eroded slowly, slowly one by one, and as a mass, it will result in a greater loss of topsoil. So it will be usually filled up in the lakes or in the reservoirs or in the areas where the water is having uniform steady state flow. So here it is estimated that there is 75 billion tons of soil is eroded from the land around the world every year. So the fact that the data collections on soil erosion is usually capital intensive and as well as time consuming process. So if you try to measure, or if you try to find out soil erosion manually by human help, it will be very difficult for you, because rain is a phenomena which induces a lots of soil erosion to the greater extent, and added to its soil erosion capability, the human activities on the soil is becoming as a catalyst. For example, construction, plowing, gardening, and any other replanting, harvesting. So when you harvest, automatically you will leave the shoots. The roots will be over there in the field itself. Then most of the time, the shoots will be burned down, or otherwise it will be removed by some other mechanical processes for recultivation of the area. So if you burn it, again it will lead to air pollution. If you use any other mechanical process, you need to pluck it out with the help of plowing machines and any other mechanical equipment. Again it will lose the topsoil. Then while raining or even through irrigation, the topsoil gets eroded. Then remote sensing and GIS are two very two tools, or one is the method for data collection and the other one is a tool or software which will enable manipulation, or you can make calculations of missing out data, of spatial data and any other type of data. And when you have the real data or collected data, then again you can be able to use it through the GIS software. So here the ability to overlay and differentiate different characteristics of the land and soil makes it more feasible through the GIS software to find out the soil erosion, to carry out a suitable soil erosion modeling. Then the study area which is taken here is highlighted in the state of Jharkhand, and here this is the location, this is the approximate location where the where the Baraka river basin gets covered. Actually, river basins are natural boundaries. It is not administrative boundaries. So here we can have administrative boundaries, but in reality, nature will not follow administrative boundaries. It follows its own natural boundaries. So a basin is an area delineated by the catchment or the collection of water. So whatever the rain or whatever the water droplet which is falling in this area will get connected through this funnel shaped or basin or pan shaped area, and it will be flowing through a river. So here we are having Maithan Dam and Tilaiya Dam. So here there will be Maithan Dam here and Tilaiya Dam over here in the study area. And apart from this, the study area is also having many ponds and lakes and settlement areas. So then next, the approximate length of the study area is 225 kilometers. The catchment area delineated is 18,000 kilometers square. It lies in the coordinates, which means the center point of the area is this one, 23 degrees 42 minutes north, 86 degrees 48 minutes east. So there's, you need to know the soil types that are present in the Baraka River Basin, because every soil will behave differently towards the water and its reaction of erosion and topsoil loosening. And also the bearing capacity of the soil also changes. So mainly the predominant type of soil which is available here in the study area is red soil, and second one is red loamy soil. The loamy means the condition where there is a large quantity of clay is available, then it becomes this loamy soil. The next comes the loose sandy soil. The third type of soil is loose sandy soil, which is highly susceptible for erosion. The next comes the lateritic soil. So when you talk about the lateritic soil, this is actually a soil which is rich in iron content, but it is having poor cohesion with each other. The next comes the methodology. So this is the entire workflow methodology which was carried out in the study area to run the Russell model. So here you'll be able to see here the study area, it will get selected. Then next, the data collection needs to be performed. Then the first data that is required is rainfall data. Then the next data is soil data, or the types of soil classification data for the study area needs to be acquired. The next comes the land use and land cover map. So this is the dynamic data which will get changed according to the land use year by year. So some land can be classified as vegetation 2 or 3 years back. Now it would have got settlement, or the agriculture would have been taking place, or any other activity, for example industry, road, any susceptible human activity can take place in the given land. So that is the reason why you need to update it, land use land cover map, each and every year to the minimum level. Next comes the valuable digital elevation model. So this digital elevation model is very, very important, because if you don't know the elevation and the slope of the area, then you will not be able to find out the other important factors which will influence the soil erosion. So using rainfall, you will be able to create R factor, and using the soil data, we will be able to create a K factor in the form of maps. So R factor map will be created, K factor map will be created, and land use land cover map. By using the land use land cover map, we will be able to create the C factor map. Then by using the LS factor, which means longitudinal section slope or land slope map. So we'll be able to create the LS factor and the P factor. So then the sediment yield is the product of all these factors that will be resulting in the sediment yield calculation. Then finally, you need to overlay all these factors. Then that will result in the estimation of sedimentation through the model. Then next comes the data source. So you should be able to see. So this is the data sources links which I have used. So some data is collected from foreign university and foreign websites, and some data is collected from Indian websites. So you'll be able to see that the cru.uea.ac.uk, there we collected the rainfall data, and again we collected the basic data like other temperature and other data from the Columbia University, and we collected the few data from India Water Portal and NASA. We have collected the satellite images, and data.gov.in is again used to collect the historical data. Then JRC Europa and FAO will provide you Food and Agriculture Organization will provide you the soil data, and ISRIC data will provide you the global soil database. And ISRO, from ISRO we have used the land use land cover map, and Earth Explorer, again usgs.gov is used to collect data regarding the cross verification of satellite images and the data accuracy. Then next comes the ArcGIS 10.30 software is used to carry out this entire work. The next comes the methodology. So there are many other models available for measuring soil erosion or modeling soil erosion, but to limit the presentation within the given time, I have taken only one model. So apart from the other models, there is also modified universal soil loss equation, ASIL universal soil loss equation, and SWAT, and there are many models which are available. So in the case of from the perspective of a researcher or a student, you can go through those data, and more or less the data required are presented over here. From this slide you will be able to get to the maximum 99% of the data that is required to run this model, all the other models also. So here you will be able to see the Russell equation is explained as A is equal to average soil loss equation ton per hectare per year. So R represents the rainfall. R in this equation, rainfall will give you the erosivity factor, and so that is megajoules per megajoules millimeter per hectare hour per year, because rainfall is calculated in hours. Okay, the next comes the K is the soil erodibility factor. So the soil erodibility will be calculated in tons per hectare per hour, again per hour. Then with respect to the megajoules per millimeter. Then length of slope, that or the steepness factor. So again it will be a dimensionless factor. C is the cover management factor, that will represents the surface cover of agriculture practice. Then next comes P. So P represents the conservation practices factor. Suppose there may be agricultural practices which will be taking place in the entire region without any conservation activity also. The vegetation cover or the surface cover of the area determines the nature of erosion which is possible. Suppose if you take the constructed road, and if you take constructed buildings and parks, so there are human settlements or human concrete buildings where the erosivity will be zero. But when you take a wheat field or a wheat cultivated field or any other cash and food crops cultivated field, the erosivity or the cover management the cover management factor changes, because there are maximum possibility for erosion in the canals and in the wheat cultivated zones, food and cash crop cultivated zones. For example, best example is sugarcane, rice and wheat. So these are all crops which will allow or which is susceptible for maximum soil erosion. The next comes the rainfall erosivity factor. So the rainfall erosivity factor is the 81.5 plus 0.375 multiplied by mean annual rainfall, and the annual rainfall will be taken in millimeter. Again, the soil erodibility factor so is equal to KFC sand dot FCL minus F minus SI multiplied by F ORGC multiplied by F HIS, and so you'll be able to see the F sand, which means the parameter provides low erodibility of soil with high coarse sand content and high erodibility for soil with low sand content. So here, when the soil is coarse and when it is having the soil with high coarse sand content, so this will provide a parameter, and for the opposite also it will provide a parameter. Then next comes the parameter FCL-SI. That parameter provides low erodibility for soils with high clay content to silt ratio. So when the clay and silt ratio is high, So this parameter will add up a value. So the parameter, the FORGC provides parameter for the low erodibility of high organic carbon content, because whenever we talk about agricultural land, so the land will definitely have organic content, so that will represent the carbon content in the soil. And then F HIS HI sand, which represents the parameter that reduces the soil erodibility for very high sand content. Okay, so when you substitute these values as parameters for the study area, you will be able to create a map. The next comes the topographic factor, or LS factor, land slope factor. And here this again needs to be corroborated or substantiated with flow accumulation multiplied by the cell size. This cell size represents the size of the cells which you are assigning for the study area. So you can take it by 30 meter by 30 meter, 10 meter by 10 meter, or 5 meter by 5 meter. When you start reducing the cell sizes, the accuracy will improve, but at the same time the load in the system will be increased, and due to this particular nature, the model will take very long time to run. Again, you need to have very high level of processor and very high RAM quantity, RAM content in your system. The next comes sign of the slope to the power of 1.3, and for this first parameter that will be to the power of 0.4. The next comes the crop management factor. So this crop management factor is taken from United States Department of Agriculture 1951, and again this is substantiated, or this is tested by the scientist David in the year 1988. So finally the C factor is being derived. So when you go for row cropping in an area, then the C factor is 0.24. When you take pasture means grassland or hay, and then it will be 0.050. And water and wet areas, so already because the land is getting submerged, we will assume that there is zero soil erosion possibility. The next comes urban low density area, then that becomes 0.03, and urban high density area, which means completely concreted surfaces, which means there is no green surfaces at all, or soils are available at all, then this becomes zero. The erosion becomes zero. Deciduous forest, then the possibility for erosion is 0.009. Then the evergreen or coniferous forest is susceptible to have 0.004, and the mixed forest. So where there is no clear demarcation of forest, on that condition you can assume a C factor of 0.003. The next comes the conservation support practice factor. So the assumed P factors for different types of management practices is given by the scientist David 1988. So you'll be able to see that when you go for conventional tilling method, so then the P factor is having 1. Then the zoned tillage, which means there are some areas you are allowing for tilling works, then the factor gets the value gets reduced to 0.25. Then mulch tillage means you are mixing the soil with organic and carbon content, then the P factor has increased to 0.26. Then the minimum tillage, if you have minimum tilled area, then the P factor is assumed to be 0.5. The next comes the results. So when we have taken all these values for the study area and we have plotted it in the GIS software, then the resulting K factor. So this K factor quantifies the soil loss per unit energy of precipitation. Per unit energy of precipitation means assume that 1 millimeter of rain for 1 meter square of area, so that will be taken into consideration. Okay, so that is the per hectare of area that will be taken into consideration, not 1 meter square. Then that causes soil loss, erosion. Okay, that causes soil loss or soil erosion. The highest K factor value observed in the study area is 0.15 tons per hectare hour. Again, per hectare, megajoules per millimeter. Okay, so for 1 millimeter of rain with this energy amount, per energy amount, then the per hour of rain per hectare, the resulting or the susceptible erosion is 0.15 tons for the particular soil type, because soil type also influences the variation. And the lowest value observed in the study area is, you will be able to see that 0.13, and the medium value which is observed is 0.14. So the results of K factor ranges are provided in this figure. Next comes the if there is heavy precipitation, so the soil particles will get easily eroded off due to high runoff, and the high runoff flow results in significant sheet or rill erosion. So sheet means, assume a sheet of soil over the top surface is getting eroded, and the rill represents the the loose top soil which is getting eroded in the form of different kinds of sheets, different layers as sheets. The highest R factor value observed in this study is 1000 megajoules millimeter per hectare per hour of rain in this entire year. The lowest value is 260 megajoules. So this is the lowest value is provided in the dark color, and the highest value susceptible for erosion is provided in the light shades of the purple color in this drawing. Then next comes the LS factor, land slope factor, or simply topographic factor. The slope length and the gradient represents the angle of the land, and the slope length represents the length of the particular land in that angle. So that that influences the surface runoff velocity. And why? Because for example, it can be a 100-meter length of land with just 1 or 2 degree slope, then the susceptible erosion will be very less. Assume that if there is 30 degree to 45-degree slope of land with for the same 100-meter length of the land surface, the susceptible erosion will be very high, and also it is controlled or it is influenced by runoff. If there is heavy downpour of rain with a very fast runoff flow, then depending upon the slope of the land and the length of the slope, then the erosion will also increase or decrease correspondingly. The topographic factor again includes the slope length factors and the slope gradient factors S. So that is the reason why it is called as LS factor. So L represents the slope length, and the gradient is represented by S. The highest LS factor observed value in this study area is 55%, and the lowest value is 0%. So which shows that there is also area which is present in the study. There is also locations in the study area where we can expect 0% erosion also. This 0% area is mostly the constructed high density urban settlements or roof to roof connected area. So most of the study area is having influences for very less erosion, but you'll be able to see there are red color lines which is present in the study area, and yellow color, and the dark black lines. So this dark black lines and this green lines represents the area which is susceptible for very high erosion. So actually these were all these lines represent the locations where there is maximum runoff capacity depending upon the slope. The next comes the C factor. So the crop management factor is again plotted in arc map using the values in the table 1, which is previously shown to you. So you'll be able to see here the C factor and the P factor. So based on this value, we have applied. So based on the land use land cover map, we have applied these factors to the study area, and we obtained these results for the C factor and the P factor. So first we will discuss about the C factor. The C factor represents the crop management factor, and again this is plotted using the table which is previously recommended. So you'll be able to see the areas of 0, and the maximum value is observed between 0.1 to 0.4. So 0.1 to 0.4 represents the values are mainly between the pasture and hay. So the row crops, sorry, the pasture and the row crops. Row crops are given 0.24 and the pasture is given 0.05. So that being the condition, we'll be able to see that most of the area which is present in sorry most of the locations in the study area which is present inside the boundary is susceptible for the C factor erosion, or due to the crop management practices soil loss are very high, because the agriculture is the major source for food for these peoples, and due to that reason the land gets tilled again and again, and that is the reason why you will be able to see a maximum pink area which is representing the possibility for what to say that soil erosion. Then you will be able to see the P factor. So the P factor again, this represents the tillage and residue management values that are given in the table. So you should be able to see here conventional tillage. So here this peoples, which means the peoples in the study area are practicing conventional tillage, or they doesn't practice zoned tillage or mulch tillage or minimum tillage. These peoples are practicing conventional tillage for their agriculture. So the conventional tillage means they will be using human method of tilling, and at the same time there will be no differences in the tillage area. So the surface of the land gets disturbed again and again easily due to the agricultural activity and the human construction and any other mining activity also. So due to this reason, you'll be able to see the maximum area in the study is susceptible for soil erosion, and there are very less area you'll be able to find which are favorable to soil erosion. Then finally all these different layers are overlaid and the model is run in the ArcGIS software. So when you run the model, so you'll be able to see locations where it is susceptible for soil erosion. So there is also locations in the study area where there is zero soil erosion probability, and to a maximum of 700 tons per hectare per year, and the average estimated value is 6.19 tons per hectare per year. So this 700 tons is assumed to be the maximum worst case rainfall and worst erosion situation, and this 0 tons per hectare per year is obtained from the constructed area. The high density urban area will not yield to soil erosion, but the area which is susceptible for soil erosion will be having maximum possibility when the very high slopes are available, very high rainfall is available, and the expected runoff goes beyond the planned or manageable runoff value, and to the average. So it is assumed that, or it is estimated that the average value is possible or susceptible to be eroded in the study area, which is 6.19 tons per hectare per year. So this 0 to 6, so you'll be able to see the pale green, the pale yellow areas in the study area which are susceptible for this average value of erosion, because the majority of the area, sorry, the majority of the locations or the majority of the cells present in the study area is susceptible to have average or below average soil erosion from the result, but at the same time the pixels or the cells which are susceptible to have greater than the greater than the average soil erosion is given in yellow color, or in the yellow tone. You will be able to see that area covers most of the locations, and the area which is susceptible to have 3 times to 4 times or even up to 10 times the average soil erosion is almost few locations. and the area which is susceptible to have more than 10 times to 100 times soil erosion is again 3 to 4 approximate. It is about 3 to 4. Then two, which means more than 100% to 1000% of soil erosion is susceptible to be happening in one or two locations in the study area. And most of the times this practice or this soil erosion is again controlled or this susceptible to pasture land. So you'll be able to see that the entire study area is covered with grass and grass type location. So most of the areas are used as pasture lands or for grazing, where there will be grasses are available. So here the susceptible soil erosion is approximately or about less than 6 tons per hectare per year. But the soil erosion in the grassland is slightly more. In the pure grassland, it is slightly more. The pasture land will be having a mixture of grasses and other herbs and other plants. Then, when you talk about orchards are intermediate regions where it is having susceptible soil erosion of 30 tons to 88 tons per hectare per year, and the soil erosion range is very high or high in the region of Indian grassland. So there is the grass which is called Indian grass, which is able to grow in a sandy soil. So which is favorable condition for the grasses to be grown. So that is the region where it is showing, the model is showing very high or not very high, high level of soil erosion possible. Then the soil erosion is very high, which means in the entire study area, this this blue cells represent the locations where it is possibility or where there is possibility for very high soil erosion. So, and those areas are range and Indian grassland, which means range and Indian grasses are good fodder. Fodder means the food which is used for cattle and other kind of grass eating animals, even horses, donkeys, and everything will get covered into that particular criteria. So this will be used as fodder. So most of the times the peoples are growing this kind of grasses for fodder, and they are harvesting it to feed their cattle. So due to that reason, what happens here is that the susceptible area is having range and Indian grasses, and next falls with the Indian grasses. Again, these lands are grazing lands. So there is ultimately requirement to monitor and manage this grasslands and to provide fodder. So because we cannot stop fodder growth also, because it is very, very important for the farmers and the poor peoples to feed their cattle. So if it is managed, so if this problem is getting managed properly, then we can be having, we'll be able to save very high quality nutrient rich soils. So these are all the technical reference papers what I have used over here. So thank you for your patience. Now I request the presenter to open the session for questions.
Yes, sir, we have two questions.
Yes, ma'am.
One is from Agra Chakrabarti. He has asked that minimum time required for this project, and because we need to observe the change of soil profile over a certain period of time. So, what is the minimum time that is required for the project which you have explained?
Okay, ma'am. Is the slide visible to you right now? What I'm showing to you right now? Is my screen visible?
Yes,
Yeah.
yes.
First, it starts with the data collection, ma'am, and the period or the time period what you are willing to run your model. For example, if I am willing to run the model for consecutive 10 years, then I need minimum yearly rainfall, and the soil is not going to change, and the other data. For example, you will be able to see here the rainfall is the rainfall will be continuously changing. It will be dynamic. And for example, assume that if you are going to run the model for 10 consecutive years, then you need to collect 10 years rainfall. The soil is not going to change. Then the topographic factor will be changing, because every year there will be new constructions, and the crop management factor will not change, but the crops on that particular year will be changing continuously. For example, everyone will not follow the same type of cropping method. So you need to be classifying the cropping type first, then next the tillage practice. So more or less the tillage practice can be identified easily with the crop pattern type itself, because for cultivating wheat and rice, they will be plowing the ground. So plowing the ground means you are disturbing the soil almost 1 to 2 feet in depth approximately. So all these things. So for the 10 years, you need to have cropping pattern data, and for the 10 years, you need to have this topographic data, which will be you will be getting it from land use, land cover, and for 10 years rainfall. The soil is not susceptible to change for the majority of the time. So once if you have created all this data, then you can run it. So this model, what I have shown to you is it has been run for 10 years. But for every year you need to do it, and finally average of the values can be obtained.
Okay. Okay. So that means we need to take a decadal data sets.
Yeah, it depends. It depends. For example, if you're doing it for a PhD level, or if you're doing it for MTech level, you can reduce it to 10 to 15 years. But when you're going for the PhD level, you need to observe it minimum 30 to 40 years to confirm it for the soil erosion.
Okay. Okay. The second question is from Mahinder K. Singh. He's asking that, sir, soil erosion is most significant cause of land degradation and desertification in specifically Rajasthan. So how this can be prevented in case of Rajasthan?
Yes, ma'am. In case of Rajasthan, first you need to identify the land use, land cover pattern. For example, if there is constructed area, if there is urban area, then there is no possibility for soil erosion. But when you go to the other side of the picture, so there is a large desert area. So when you are having a desert area in Rajasthan, that is highly susceptible for dust and soil particle erosion easily. So most of the time, the erosion in Rajasthan is aeolian type, or which the erosion which is influenced by wind. So to stop wind, either you can go for physical structures like construction of concrete walls, or otherwise the better way and the easiest way is to grow trees. So first of all, you should be able to identify the trees. For example, Bina Christi. So that is a variety of thorn. It will be able to grow in any location. Usually found in the Negev deserts of Israel. So you can grow them over there to reduce the soil which is getting carried away. And most of the time we forget that we need to, whenever there is rain in the desert, you need to channelize the rain, and you need to construct coffer dams, and you need to construct small causeways and small structures that will be able to store water even for a very less amount of time. So by that you will be able to provide water for the natural grasses which will be able to grow in the location itself. For example, if you take the case of California, most of the time the Californian surface will be dried. It will be deadly dry. But when it rains, there will be beautiful flowers. You will not be able to find out in any gardens. So such kind of transformation will take place. So for that you need to start saving water. Then when you go for the agricultural practices, and almost you should practice, or you should go for cropping which follows multiple patterns. Suppose if one farmer is doing tillage, then the other farmer should use the other kind of cropping pattern. So when you mingle different type of cropping patterns together in the same location, then the soil erosion is found to be very less. So these are all the methods where you can do it practically. But for analysis, you can do the same kind of analysis with different models in Rajasthan. for the most notable area where there is possibility for high soil erosion.
Okay, thank you, sir. The next
Thank you.
question
Thank you.
is from Bhartendu Sajan. He's just want to know that can we predict the soil erosion? Which model is to be used for soil modeling?
Soil modeling. Yeah, I told you that the first of all the soils are not same. Please try to understand. So the soil is getting classified on engineering basis into three different kinds. So first one is you'll be able to see sand, and next one is clay, and the next one is silt. So whatever soil content, if you're taking into consideration, so this 3% defines the engineering properties according to what I have studied. So on that being the foundation, you should be able to identify the soil and its respective behavior, because the behavior represents the soil's nature, reaction with the water and also with air or to the runoff. So if the clay is having very high content, or if there is very high clay content, that soil is poorly suitable for agriculture, and but that is highly suitable to store water. So the depending upon the soil properties, or based upon the soil properties, the erosion will also change. So that is the reason why I cannot, not only I or any scientist who is working in the soil cannot recommend one universal model where all the soils can be studied. So first of all, you need to work with minimum 3 to 4 models. Then you need to decide upon which model is getting more related, or which model is getting will give you more practical solutions. And again, we are also getting restricted by the data availability.
Yeah.
So in Indian context, most of the times all the data will not be available in the public domain. So if you're going for data, you need to write a letter and you need to wait for 6 months or 1 year. By the time your project will be over, you have to get your degree. So there is lots of things which is abstracted over here. So from my point of view, I can give you that first take 3 to 4 models depending upon the data availability, then work on it, then try to find out the practical relatedness of your model to the data. Then it will be more applicable to get into a conclusion, because every soil is different, so the models needs to be different.
Okay, thank you, sir. Thank you. I think now he is able to, understand which model has to be applied in what kind of soil. Next question is from Dr. Suman Sinha. He has two doubts. One is that final results to show that there are few pixels in severe soils erosion category blue, and just next to that we have at least categories class, means how can this vary just after 30 meters? Second,
How to classify this image? So that's what the question is. It.
yes.
Yeah,
And
actually
second,
these values, first let me be clear, these values are from the model outputs. For example, when you take 0 to 6 or 7 to 29 or 30 to 88, 89 to 285 and 286 to 700, all these values are output from the models. So this is not user classified values. And moreover, this model or any model will run based upon the data accuracy what you provide. So most of the times we have poor data, and also we in this case, in the beginning of the slide, I have given you the soil type: red soil, red loamy soil, loose sandy soil, and lateritic soil. So all these types are majority of the soil types which is present in the study area. But when you get into the field, when you reduce your study area within a village, then you will be able to see again there are some kind of left out soils or some kind of soils which are new to the zone. So you may have a question how these new soils are getting into the scenario. These soils actually not we, especially Bihar, Uttar Pradesh, and Jharkhand. So all these rivers, all these states are beneath the mountains of Himalaya, the Himalayan ranges. So whenever there is a rain, whenever there is a heavy flood, the Himalayan rocks again broken down into pieces, and the silt, sand, and the soil which is getting deposited through River Ganga and other tributaries will cause a change in soil type also. So that is the reason why you will be able to see this data, this output data. We have carried out a 30-meter by 30-meter cell size analysis, and based on the provided data and based on the cell size, this output is being arrived. Suppose assume that if I am reducing the cell size to 5-meter by 5-meter or 10-meter by 10-meter or even any other size which is less than that, then the processing time will also increase. The RAM taken by the RAM available in the computer will be overloaded, and you need to have a suitable processor also. So based upon the available equipment and based upon the processing capability, we have given the cell size. So that is the reason why you find a few cells, but if you increase the cell size, there will be many more number of cells also available.
Okay. And so secondly, how is the field verification conducted in such kind of studies?
Yes, ma'am. In this case, again, if you go for field, it will be impossible, because when you complete visiting your field for one particular soil type, by that time there will be one more seasonal rain.
Yeah.
So on that case, you need to depend only on the remote sensing data, and there are soil types which will have different reflectivity properties. For example, when you take lateritic soil, the lateritic soil will be red in color. It will be high in ferrous content. So that is the reason why you will be able to see red soil whenever you come across the red soil. But when you see the particular soil, or when you observe the red soil through the infrared spectrum of the satellite data, or the infrared data which is present in the satellite spectrums, so the soil will be dark in color, because the ferrous or the ferric content in the soil absorbs the infrared waves. So that is the reason why the soil which is having very high content of iron or high organic content will become dark in the color. So this kind of patterns can be verified with one or two site visits. And again, every soil, for example, sand, when it is dried, it will reflect more of the infrared spectrum. So it will be available light red in color, or light white color in color, more or less related to white color. The sand is dry. If the same sand, when it is wet, it will be slightly dark in color. So likewise, every soil has different behaviors. So based upon the major portion of the soil that is visible to you in the remote sensing data, you can select or you can pick few locations of the study area, then you can verify them. So this is possible.
Okay, thank you, sir. Last question from my side. Nowadays, we are seeing that due to heavy rainfalls in most of the hilly areas, we have soil erosion kind of things.
Yes.
So, what could be the thing so that we can go for the preventive measures for those kind of
Yes,
erosion?
ma'am. First of all, you can find out suitable vegetations that can be grown in the area. That is more important. And you cannot avoid soil erosions which are taking place either in Himalayas or even in Assam or any other, because we are taking more ores, for example, coal, iron ores, and many other metals and materials are being taken out of the hills regularly. So if you stop it, then again the peoples will starve without having any economical flow and money. So that also needs to be maintained. So whenever they are mining it whenever they are mining the location, then after, or when the mining gets completed, you need to start planting indigenous plants. Indigenous plants means the plant varieties which will be growing over there in that same location for more than 1,000 years or 2,000 years. That will be old plants, which means that will be called as indigenous plants. So those indigenous grasses are covered with that will be able to grow in location again. And the grass seeds are very easily spreadable, and the indigenous trees, so that needs to be planted again in that locations. to stop the erosion and landslide. So this is the only possible way. Otherwise, we can construct concrete, we can go for sheet piling, we can go for any other costly measures, but this will be that will increase the cost of maintenance again and again. And moreover, when you disturb any surface, natural surface, you need to ensure that very deep rooted trees must be planted over there, because these deep rooted trees will form network of roots which will be able to capture the below underlying rocks and soil together for a very long period, so that we can get benefited in both the ways. We can reduce the carbon and also we can improve the slope stability also. So this is the only way which is feasible. There is also other technical methods. You can go for geotextile reinforcement. You can cover the surface with steel nets, or you can go for sheet piling. There are screen piling. So we can do many other measures, but those are costly and which is not affordable for us.
Thank you so much, sir, for such a nice explanation of all the questions. I think all the people, they are satisfied with the answers and they have learned a lot. I am getting continuous message for the session that is very excellent and very informative session. Thank you so much.
Okay, thank you. Thank you. I'm signing off.
Yeah. Priyanka.
Yes, ma'am. Thank you. Thank you, ma'am, for such a beautiful question and answer session. And thank you, Gopikrishnan sir. It has been a very informative and educative session that we've learned a lot. And moving forward with today's event, we are moving to our second speaker, Muhammad Sayeed ul Hasan, Assistant Professor from Department of Civil Engineering, Aliah University, Kolkata. He did his Bachelor of Technology in Civil Engineering from Aliah University, Kolkata, followed by Masters in Environmental Science and Technology from NIT Durgapur. Currently, he is also pursuing PhD from IIT Kharagpur. He is a passionate and motivated, young researcher, and he is also keen on research, collaboration, and outreach by participating in numerous national as well as international conferences and workshops. He has several recognized and published research work by many reputed peer-reviewed national and international journals. He is a strong believer in interdisciplinary research, and his area of interest and expertise are in the field of climate change, groundwater exploration, optical and microwave remote sensing, GIS, hydrometeorological extreme, spatial data science, within the broad spectrum of environmental engineering and natural resource management. With this thought, I would like to invite Muhammad Sayeed Ul Hasan to take forward today's event. Sir, you're most welcome.
Good morning. Am I audible?
Yes, yes.
First of all, I am thankful to the BASE Center for Climate Change and Water Research, because I started my career from this institution, and I am really thankful to Dr. Suraj sir and Shruti ma'am, who continuously guided us from beginning of our career. So without wasting our time, so let's start the session. Okay.
Yes, sir. Sure, sir.
Is it visible?
Yes.
Okay. The national webinar is on remote sensing and GIS for urban studies and environmental modeling. So as we have concerned about the environment, so I think water is a benchmark to decide the any development and economic prospects of any countries or region. So from beginning of the world, and even if we go to the history like Roman civilization, Harappa civilization, and Indus Valley civilization, whatever the civilization taking place, they are definitely beside the any river bank. Okay. So the resources which we utilize for as agriculture purposes, as well as for drinking purpose or domestic purposes. So water is a key element. for survival of any living organism. So if we see the contribution and the distribution of water resource, so how it is especially varied. So first of all, the total water resource which is available on Earth. So if you see, this is the studies by Glick, that ocean contribute 96%, and if you see the fresh water, that is the 2.5% only contribution. So in 2.5%, if we see the fresh water, that is the glacier, that is the 68%, and groundwater is 30%, and surface water like lake and other things, that is contributing the 1.2% of water. So apart from 1.2%, surface water and other fresh water, that is the ground ice and permafrost 69%, and lakes 20%, and atmosphere 3%, and rest of the things contributing a little more. So the important thing is that with global warming and all those things which we are going to encounter with, like anthropogenic activities, these resources are drastically changes in the concentration. So if we see, like these are the studies which are carried out by various researchers globally, and this paper is published by SH in Nature. Okay, so if we see how the depletion of water, total water, groundwater resources are depleting at what rate. So if we and parallelly, if we see, that is that there is a equivalent sea level rise. So sea level rise is another major concern when we are dealing with climate change, because there are lots of studies are carrying out as per IPCC and another organizations, that due to changing global warming, the sea level is going to be rise, and many of the island city and those cities which are nearby the coastal areas, like even Kolkata, Chennai, and most of the countries of Indonesia, Malaysia, and even Bangladesh, they are more prone to sea level water rise. So these are the more governing and most challenging situations currently the peoples are facing around the coastal world. So if we see the recent study, that is the Pokhel. So how the depletion of water takes place from 1950 to 2010, and the global groundwater has declined 4,500 cubic meter from 1900 to 2008. So this is one of the another study which is carried out by the Rodel from the NASA. If we see, that is the 23 and 24, because most of the participants from Southeast Asia and especially from India, so we are much aware about the Ganga and Brahmaputra basin and Indus basin. So these are most prone groundwater as well as in water scarcity region. So if we see, that is one of the report which is published by Water Resource Institute risk in 2019. So 54% of India faces high to extremely high water stress. So the water stress consider both your surface water availability as well as groundwater availability. So if we see, that is the northwestern part is highly affected. Then if we come to South India, then these regions are also highly affected. And if we look into the some portion of lower Ganga basin and Damodar, so if we see, that is the Bankura region and some Jhargram region are also more prone to groundwater water stress region. So several attempts have been observed on assessing the climate change and human activity induced groundwater depletion, because lots of studies are also showing that there is a tremendous increase in surface temperature and other human activities like land use change dynamics, like we are converting our forest area into agriculture area. These things are also changing, because food security is one of the important concerns. So currently numerous studies are going on groundwater drought using empirical evidence corresponding to anthropogenic activities. So the global climate observation system considers groundwater as an essential climate variable for terrestrial hydrosphere. So when we talk about the essential climate variable, that is the ECV. So definitely we are much aware about the precipitation, temperature, and other parameters like relative humidity, solar radiation, wind speed. So these are the essential but by the concerning the groundwater, so GCOS stabilized as groundwater is also as a essential climate variable. For this study you need to have a volume, quality, quantity, recharge. These things you need to have to concern when you are dealing with the groundwater as a essential climate variable. So these are the some of the reports and publications and related to some newspaper cuttings. So how the effects are going on? So most of the people from Kolkata, they are thinking that we are from Kolkata, as we are having the lower Ganga basin and we are plenty amount of water, but availability of water is different from the quality. So when you are dealing with groundwater, so you need to have a both concern. One is the availability of groundwater, another is the quality. So if we see like in West Bengal, the boundary region like Nadia, the portion of South Chobis Pargana and Murshidabad, Malda. So along the boundary, they have the high concentration of arsenic, but they have the availability of water, but they can consume it. So this is the major challenge. Whether somewhere there is a portion of availability of water, but the quality is not good. When there is some quality is good, but the availability of water is not there. So we need to have to check when you are going to study any groundwater stress analysis. So because this session is from remote sensing and GIS perspective, so many of students from non-GIS background, geoinformatics background. So just I want to overview in a single slide. So there are different types of remote sensing. One is the optical remote sensing, thermal remote sensing, microwave remote sensing. Depending upon the application, people go and to complete their objective. So in the flow chart we are going to represent is that is the optical remote sensing. So whatever the energy we are getting from the sun, then it reflected to the satellite. Depending upon the intensity, the characteristics of the digital number of the that image or the pixel value, the data get transmitted to the stations. Okay, then after stations that we are going and process, that is the data pre-processing, and that is the cloud-based server. Normally we are dealing with a USGS, Alaska, and another platform like right now there is a European Space Agency for Sentinel data, USGS for what you say Landsat series, and the Bhuvan for ISRO based satellite. So these are the platform, and after the data processing, then you go for the data processing and analysis. Depending upon the objective, in what domain you are going to apply your data and your prerequisites. Suppose someone is going to work on flood, so they have definitely that kind of variables which is affecting the flood intensity and the prosperous of flood, like extent of flood. If we are going to deal with only the extent of the flood, then you definitely go for the Sentinel data. And if you want to do the delineation of flood prone areas, then you will go for the multi-criteria decision making. And similarly, if you want to go for the urban planning, then you go for that kind of data, like the resolution is important thing. But if you are going for the land resource management planning for over a large scale or in a basin area, then you can continue with some course resolution also. So it is important to understand what is our objective and at what extent we are going to work or analyze the data. Now, as this is one of the short video, just I want to run. Don't focus about whole world, just focus on India. So this is one of the data set, that is the gravity recovery and climate experiment, and FO is just the follow-on mission. This data set is developed by NASA as well as the Germany Space Application Center, and which is launched in the year of 2003 in the month of April. So till 2017, the satellite is working well, but from 2017 to 2018, the another satellite of Grace F4, that is the follow-on mission, will launch, and that's why we have considered Grace F4. And the spatial resolution of the data, spatial resolution means the pixel size of the data is that is a 0.5 degree. Initially, when they launch, they have the resolution of 1 degree. After pre-processing, then come it to 0.5 degree, 0.5 degree currently, and there are lots of data series depending upon the application. One is from NASA, another is GSS, and another is the CSR. These are the data showing the total water storage. Total water storage means what? When you are having the surface water, groundwater, as well as soil moisture, and the region which is having the glacier, so it also consider the glacier also. So if you see that India in a Himalayan regions or South East Asia, these are the most vulnerable to the groundwater resources, because the thing is that there is climate change and lots of challenges and issues, and global warming. Even the urban heat island is also affecting the overall scenario of India due to rapid development in a land use pattern and all those things. So these are the governing pattern, and most of the participants from early career research, from that figure you can, if you want to work on climate change and other things, so you can easily figure out which study region or which area is more prone to climate change and groundwater resources. So accordingly you can find out your study and you carry out your research. So before beginning the, because my motto is to develop the interest in the field of remote sensing and GIS and application in remote sensing in natural resource management. So first and foremost thing, I suggest if you wish, then please go to watch this movie, that is the Swadesh. In everyone life there is some inspiration and some motivation. From there one continue to work. So that is the movie which reflect and develop interest. We need to have to study in the climate change studies and the drought parameters. So I personally recommend you to go and watch this movie. And initially what they designed, that guy is working in NASA, and how the satellite, that is the GPM, that is the global precipitation measurement, and they represent that satellite in 2004 that is this movie released. But in 2011 and 14, when you go to utilize that data set which is shown by the movie, so there is a different happiness. Oh wow, I got something. And they are showing how the village peoples are affected by drought, and how the agriculture productivity is reducing. So one can easily watch how the people from the community, from the low economical condition, like in villages and suburban regions, so how people are surviving, and how the climate change impacting the lifestyle of the people. And the second figure, during my masters, when I visited to Bakura, which is a small district in West Bengal. So these regions are highly prone to groundwater resource, as well as quality as well as quantity perspective, and some of the childs are playing. Just I clicked it. So that is another motivation. And then after these motivation come, I put into my publication and work on it. So those who are interested for this work, I request you, and I will send the complete paper. So that is the hydrometeorological consequences on the water balance in the Ganga river system under changing climatic condition using land surface model. So as we know, and from the GRACE data, so Ganga is one of the most prone to the ground water, surface water, and many climatic activities. So the important thing is that when you are going to design any objective or any study area, so my personal view, go for the any hydrological boundary. those who want to work, whether you want to work on basin, sub-basin, catchment or watershed, so you can go proceed any hydrological boundary. I personally didn't recommend to go for any administrative boundary, because climate has their own phenomena. Either you go for the hydrological boundary, or you can go to climatical classification that is given by the Caesar. So and there is a 19 sub-basin in Ganga, and this is the map which I have produced from the ISRO published NRC report, RIS, and after georeferencing and digitizing all, then we have prepared these 19 sub-basin. Now come to the data source and methodology. The first and foremost thing in monitoring and estimation of the water budget is to delineate the river basin, as we have discussed. Now the thing is that all the availability of the data set is not possible at the right time and with the time availability, which Gopinath sir already discussed.